Hello, and welcome to this presentation of the embedded flash memory, included in all products of the STM32C0 microcontroller family. The STM32C0 embeds up to 256 kilobytes of single-bank flash memory. The flash memory interface manages all memory access, including read, programming, and erasing, as well as memory protection, security, and option bytes. Applications using this flash memory interface benefit from its high performance and low power access. It features a small erase granularity and short programming time. The interface also provides various security and protection mechanisms for code and data, applicable to both read and write access. The main flash memory is divided into 2 kilobyte pages, which can be erased independently. A mass erase feature is also supported. Flash memory access may require wait states, depending on the current CPU frequency. To reduce latency, the flash controller includes both an 8-byte prefetch buffer and a 16-byte instruction cache. These features also help lower power consumption, as they belong to the V-core power domain. In addition to the 32 kilobytes of main flash memory, the STM32C0 supports an information block that contains a system memory of 6 kilobytes, a one-time programmable memory that can store user data permanently as it cannot be erased, option bytes, provided to configure default settings for the system-on-chip IPs that are automatically loaded after a power-up reset. The system memory is reserved and contains the bootloader, which can reprogram the flash memory through one of the following interfaces: USART1 and I2C1. The first table details the memory organization based on a main flash memory area and an information block. The second table explains the granularity of flash memory operations. Programming is performed on 8-byte double words, while fast programming is done on a 256-byte row. Erasing can be done globally with a mass erase or on 2 kilobyte pages. The securable memory is aligned on pages. Write protection is applied per page, while read protection is global. Proprietary code readout protection is applied to 512-byte areas. Fast programming allows the programming of a 256-byte row, while normal programming has a granularity of 8 bytes. The main purpose of fast programming is to reduce page programming time. This is achieved by skipping the verification of flash memory locations before programming, which saves the time spent on high-voltage ramping and falling for each double word. By default, access to the flash control register is locked. An unlocking sequence must be executed before erasing or programming the flash memory. Fast programming of a 2 kilobyte page is 37% faster than standard mode programming. The mass erase time, which refers to a 32 kilobyte erase operation, takes approximately the same time as erasing a single page. Fast programming versus standard programming. With fast programming, 256 consecutive bytes are programmed at once, while standard programming uses 8-byte double words that can be located anywhere in the main flash memory. 8-byte programming is more reliable due to the verification step. It is important to note that the maximum time between 2 consecutive double words is approximately 20 microseconds. If the next double word arrives after this delay, fast programming is aborted and an error flag is set. Therefore, interrupts should be disabled to ensure this delay is not exceeded. This table summarizes the differences between standard and fast programming. Each program or erase operation can degrade the flash memory cell. Over time, As program and erase cycles accumulate, memory cells may become non-functional, resulting in memory errors. Endurance is defined as the maximum number of erase and programming sequences that the flash memory can withstand without compromising its reliability. Data retention refers to the ability to maintain a specific data pattern for a designated period. This retention is influenced by both the number of program and erase cycles and the operating temperature. The flash memory has a fixed access time, while the AHB bus frequency can be dynamically changed. That is why the number of wait states is programmable and must be set according to the actual AHB frequency, known as HCLK. Software is responsible for adjusting the number of wait states based on the HCLK frequency. Increasing the number of wait states must be done before increasing the frequency. Decreasing the number of wait states must be done after decreasing the frequency. When the number of wait states is greater than 0, the flash memory accelerator should be activated to limit the performance impact. The CPU generates 32-bit instruction fetch requests. The 8-byte line containing the requested instruction is read from flash memory and stored in the current buffer, while the requested word is directly transferred to the CPU. The next line is automatically read from flash memory and stored in the prefetch buffer. Therefore, in the case of sequential code, back-to-back words will be delivered over the SAHB until a branch is encountered. When the code is non-sequential due to a branch, the instruction may not be present in the current instruction line or in the prefetched instruction line. In this scenario, the penalty in terms of cycles is at least equal to the number of wait states. Small loops can be entirely stored in the current and prefetch buffers, eliminating the need for flash memory access. The flash memory controller also implements a 16-byte instruction cache. Each time the requested instruction is not found in the current and prefetch buffers, the line is copied into the instruction cache. If the CPU requests an instruction that is already in the instruction cache, it is provided without any delay. Once all the lines in the instruction cache are filled, the least recently used, or LRU policy, determines which line to replace. This feature is particularly beneficial for code containing loops, as instructions at the branch target address will be present in the instruction cache. Both the prefetch buffer and instruction cache can be enabled or disabled by software, as their performance impact depends on the number of wait states required to access flash memory. Additionally, the instruction cache can be reset by software. The performance continues to increase linearly with frequency when accelerators, such as the prefetch buffer and instruction cache, are enabled. The slope of the performance curve, for both prefetch and cache enabled, remains largely unaffected by the transition from 0 to 1 wait states at 24 MHz. Between 0 and 24 MHz, enabling the prefetch buffer and instruction cache does not enhance performance. This array also indicates that enabling the prefetch buffer and the instruction cache contributes to reducing consumption from flash memory accesses. Readout protection aims to safeguard the contents of flash memory, option bytes, internal SRAM, and backup registers against reads requested by debuggers or software reads caused by programs executed after a boot from SRAM or bootloader. Only a boot from flash memory is allowed to read the contents of these memories. Proprietary code protection is a method to mark parts of flash memory as execute only. Note that this type of access permission is not supported by the memory protection unit found in the Cortex M0+. The user can declare 2 PC-ROP areas aligned on 512-byte addresses. PC-ROP areas are useful when only a portion of flash memory needs to be protected from third-party reads. Write protection prevents parts of flash memory from being erased and reprogrammed. The main purpose of the securable memory area is to protect a specific section of flash memory from unauthorized access. This enables the implementation of software security services, such as secure key storage or secure boot, which is responsible for image authentication. Once the processor has exited the securable memory, that part of flash memory becomes inaccessible. The securable area can only be unlocked by resetting the device. The size of the securable memory area is aligned on 2 kilobyte pages. Additionally, code executed from the securable memory can temporarily disable debug accesses. Option bytes are used to configure the system on chip before starting the Cortex M0 They consist of 128 bytes. They are automatically loaded after a power reset or upon request by setting the option byte load launch bit in the flash control register. This capability is essential for applying new settings without needing to reset the device. This slide, along with the next two, describes the various fields of the option bytes. Bit 28 configures the NRST pin to function either as a GPIO, as a reset input only, or as both a reset input and output. When set as a reset input and output, bit 29 configures the output stage to be either a pulse generator or a low-level driver, which keeps the pin low until it is recognized as a low level. This feature is particularly useful when the reset line has a significant capacitive load. The readout protection level enables the readout protection for the entire flash memory. Level 0, no protection. Level 1, read protection. Level 2, no debug. The following transitions are supported. Level 0 to Level 1. Level 1 to Level 0, which implies a partial or mass erase. Level 0 to Level 2. And Level 1 to Level 2. PC-ROP-A start and PC-ROP-A end. Define the proprietary code readout protection address range A, aligned on 512 bytes. PC-ROP-B start and PC-ROP-B end. Define the proprietary code readout protection address range B, aligned on 512 bytes. PC-ROP-RDP allows to select if the PC-ROP area is erased or not, when the RDP protection is changed from Level 1 to Level 0. Sec size defines the size of the securable memory. Boot lock allows forcing the system to boot from the main flash memory, regardless the other boot options. The boot memory is selected using both option bytes and the boot 0 pin. This table indicates the memory from which the processor will boot, based on the combination of parameters. Note that when the nboot cell bit is set to 1, the boot 0 pin is ignored, and only the option bytes determine the boot memory. When the boot lock bit is set to 1 in the option bytes, only booting from flash memory is supported. During the option bytes loading phase, after loading all options, the flash memory interface checks whether the first location of the main memory is programmed. The result of this check, along with the boot 0 and boot 1 information, is used to determine where the system should boot from. This prevents the system from booting from the main flash memory area when no user code has been programmed. The flash memory controller supports many interrupt sources, which are listed on this slide and the next one. An interrupt can be asserted upon the successful end of an operation. An interrupt can also be triggered when an error occurs during a program or erase operation. Protection violations can also lead to interrupts. A size error occurs when the data to be programmed is not word-aligned. A programming sequential error happens when a program operation is attempted without first erasing the location in flash memory. A programming alignment error occurs when a complete double word is not provided before starting a standard program operation, or when a complete row is not written before initiating a fast programming operation. A data misprogramming error happens when data is not written in time during a fast programming sequence. The flash memory module can be clock-gated when the processor does not need to access the flash memory, as well as in low-power modes. Additionally, the flash memory module can be power-gated in stop mode. The flash memory module supports the following low-power capabilities: clock gating, flash memory power-down mode, power gating of the entire module, including both flash memory and the controller. In run and sleep modes, only clock gating is supported. In stop mode, the clocks are gated, and flash memory can enter power-down mode. In standby and shutdown modes, the power to the flash memory module is gated for both the flash memory and the controller. The STM32C0's flash memory interface supports the same features as the flash present in the STM32G0, except that ECC protection is not implemented. The cache and prefetch buffer help decrease latency and consumption. The one-time programmable, or OTP area, is used to store non-erasable data. Fast programming allows you to program a row of 256 bytes instead of discrete 8-byte double words. PCROP stands for Proprietary Code Readout Protection, which protects the code by allowing execution only from flash memory, but not reading or writing. Securable memory cannot be accessed from non-secure areas. It is typically used to perform a secure boot with image authentication. The flash memory module has relationships with the following other modules: memory protections, system configuration controller, or syscfg, reset and clock controller, or RCC, power controller, or PWR, interrupts, or NVIC, security and memory protections. For more details, please refer to Application Note AN2606 about the STM32 microcontroller system memory boot mode. Thank you for attending this presentation.